Welcome back to Share Science, the weekly science brief for July 13th, 2026. I'm Curie.
And I'm Derek.
Okay, so here's something wild. Right now, as we speak, the Earth might be creating a brand new island in the Pacific Ocean. NASA satellites are watching it happen in real time.
That's incredible. I mean, how often do we get to see something like that? What's going on?
It's happening in the Bismarck Sea, north of Papua New Guinea. There's an underwater volcanic eruption, and scientists think it could lead to the birth of a new island. It's one of those rare moments where we get to witness geology in action, and it's all thanks to satellite technology.
That's amazing. So, what makes the Bismarck Sea such a hotspot for this kind of activity?
Well, it's geologically fascinating. The area is packed with faults, volcanic ridges, rift zones, subduction zones, and spreading centers. But here's the thing. It's also one of the least mapped parts of the ocean. We've mapped the Moon and Mars in far greater detail than this part of our own planet.
That's always so surprising to me. We know more about celestial bodies millions of miles away than parts of our own backyard. So, how did scientists even detect this eruption if it's happening underwater?
They spotted it from space. NASA satellites picked up some dramatic signs: steam plumes rising from the surface, ash, thermal hotspots, and green, discolored water spreading out as volcanic minerals mix into the ocean. But the most striking thing? Huge floating rafts of pumice. That's volcanic rock so full of gas bubbles that it floats. These pumice rafts are drifting across the sea surface, and NASA's Terra satellite captured some incredible images of all this activity.
Floating rocks. Now, that's something you don't hear about every day. So, does this mean magma is pushing its way up toward the surface?
Exactly. The eruption is happening along a feature called Titan Ridge, which is about 16 kilometers from the site of a similar underwater eruption recorded back in 1972. The intensity of these surface signatures strongly suggests that magma is building upward. If it keeps going, it could breach the surface, and voila, a new island might appear.
And if it does, could that island stick around? Or is there a chance it might just disappear again?
That's the big question. If land emerges, it might form what's called a tuff cone, a volcanic structure with a vent crater that could persist for some time. But it could also be temporary, collapsing and eroding away under the waves within months. Scientists are watching closely to see how it develops. There's also a slight chance the eruption could become more explosive if seawater reaches the shallow magma chamber, but that seems unlikely here. This eruption is on a spreading center structure, which tends to produce less explosive activity than, say, subduction zone stratovolcanoes like Hunga Tonga in 2022.
There's something poetic about this, isn't there? Watching the Earth create new land. It's like witnessing the planet's own art form.
It really is, and the fact that we can watch it unfold from space just adds to the wonder. If you're curious, search Bismarck Sea Underwater Volcano New Island NASA 2026 to follow the story as it develops.
From the depths of the ocean, let's head to the outer reaches of the solar system. Our next story is about a mystery molecule that the James Webb Space Telescope found on both Pluto and Titan. And here's the kicker. It doesn't match anything in our chemical databases.
This is one of those scientific puzzles that makes you feel like we're living in a sci-fi novel. Let's break down how this detection works, because it's all about spectroscopy. When light interacts with matter, atoms and molecules absorb it at very specific wavelengths. Each molecule has its own unique pattern, a kind of chemical fingerprint. So when astronomers look at the light coming from a distant world and see a dark absorption line at a particular wavelength, they can identify what molecule is causing it.
But in this case, the fingerprint didn't match anything we know?
Exactly. A team led by Bruno Bizard at the Paris Observatory was studying Titan with JWST and found an absorption feature at 5.11 micrometers, a wavelength range that hasn't been explored much. They couldn't identify what was causing it. Then, in a completely separate observing program, JWST looked at Pluto, and the same absorption feature showed up there too, only stronger and broader.
Which rules out the possibility of an instrument glitch, right?
Pretty much. The feature appeared across two different JWST instruments, so an equipment error is very unlikely. This seems to be real. There's something on the surfaces of both these worlds absorbing light in a way we cannot explain. The researchers compared it against dozens of candidate compounds, benzene, acetylene, ketene, and others, but none of them were a convincing match.
What's so fascinating is that Titan and Pluto are such different worlds. Why is it significant that this molecule is on both?
That's the intriguing part. Titan has a thick, hazy atmosphere and lakes of liquid methane, while Pluto is far colder, with an atmosphere 15,000 times thinner and a surface covered in nitrogen, methane, and carbon monoxide ices. But both are rich in nitrogen and methane, and both have environments where sunlight and energetic particles drive complex organic chemistry. So finding the same unknown signature on both suggests there might be a shared chemical pathway producing something we've never cataloged before.
And how do scientists plan to solve this mystery?
There are three main paths. First, more JWST observations to map where this compound sits on Titan's surface. Does it correlate with specific features like dune fields? Second, laboratory experiments to recreate Titan and Pluto conditions and see if candidate molecules can reproduce the signature. And third, NASA's Dragonfly mission, which will land on Titan in the mid-2030s and carry a chemistry lab. If you want to dive deeper, search Titan Pluto Unidentified Absorption 5.11 micrometers JWST 2026.
From molecules to magma, let's talk about Mount Etna, one of the most active and iconic volcanoes on Earth. It's been erupting for thousands of years, but a new study suggests it might have a completely different origin than geologists have assumed for decades.
This is a fascinating twist in the story of one of the world's most studied volcanoes. Mount Etna is on the island of Sicily, and it's been a puzzle for geologists because it doesn't fit neatly into any of the standard models for how volcanoes form.
Let's go through those models. Most volcanoes fit into one of three categories, right?
Right. First, there are subduction zones, like the Pacific Ring of Fire, where one tectonic plate dives beneath another. Second, there are spreading centers, like Iceland, where plates pull apart and magma wells up to fill the gap. And third, there are hotspots, like Hawaii, where a plume of hot material rises from deep in the mantle and burns through the crust above it.
And Etna doesn't fit any of these.
Not cleanly, no. It's in a tectonically complex area near where the African and Eurasian plates converge, but its behavior and magma chemistry don't match what you'd expect from a classic subduction volcano. It's not on a spreading center, and there's weak evidence for a deep mantle plume beneath it.
So, what does this new study propose?
The study suggests that Etna might be fed by ancient pockets of magma stored in the region. These pockets are being pushed upward through cracks and fractures in the crust, opened by tectonic stresses. It's a completely different mechanism, more like squeezing toothpaste through a tube, than the continuous conduits we see in other volcanoes.
That's a game changer. If Etna works this way, it means our framework for understanding volcanoes might be incomplete.
Exactly. It raises the possibility that there are other volcanoes we've been misclassifying. And understanding what powers Etna is crucial for forecasting its behavior, especially for the people living on its slopes. Search Mount Etna Origin Magma Pockets, New Study, 2026, for more.
From the depths of the Earth to the edges of the universe. Our next story is about the oldest quasars ever detected, shining just 670 million years after the Big Bang.
These quasars are like cosmic lighthouses from the universe's infancy. They're powered by supermassive black holes, billions of times the mass of our sun. And their discovery challenges our understanding of how such massive black holes could form so quickly. And here's the puzzle, which is the really important part of this story. It's a genuine problem for our models. Black holes grow by accreting matter, and there's a physical limit, called the Eddington limit, on how fast they can do it. Roughly speaking, as material falls in, it radiates so intensely that the outward pressure of that radiation pushes back against the infalling gas, throttling the growth rate. So there's a speed limit on black hole growth. And when you run the numbers, it is very hard to explain how a black hole billions of times the mass of the sun could have assembled itself in only 670 million years, starting from the kind of stellar mass black hole that forms when a big star dies.
So either the black holes started out much bigger, or they grew faster than we think is possible, right?
Those are essentially the two families of explanation. One idea is direct collapse, that in the very early universe, huge clouds of gas could collapse directly into massive black hole seeds, skipping the star stage entirely. Another is that black holes in the early universe could somehow exceed the Eddington limit for sustained periods, so-called super-Eddington accretion. Finding 31 more of these ancient quasars, including 2 record breakers, sharpens the constraints on which explanation can work. Search oldest quasars 670 million years, early universe, 2026, to read the research.
And our final story, how a single fossil goose is rewriting the story of New Zealand's giant birds. Stay tuned to hear how evolution on islands can happen faster than we ever imagined. And the long-standing story on those geese is what?
The established view held that New Zealand's giant flightless geese descended from ancient lineages that had been isolated on the islands for a very long time, deep evolutionary time, allowing gradual adaptation to flightlessness and gigantism over many millions of years. It's an intuitive picture: long isolation, slow specialization.
And the new fossil says otherwise?
It does. The newly described fossil suggests that New Zealand's giant flightless geese actually evolved from much more recent arrivals, birds that flew to the islands relatively late in the story and then rapidly became large and flightless once they got there. Which means the transformation happened considerably faster than the old model assumed. Losing flight and gaining size doesn't necessarily take tens of millions of years of gradual drift. Under the right conditions, an island with no predators and abundant food, it can happen quickly.
Which is a broader lesson about evolution on islands, isn't it? That the pace can be much faster than we assume.
Exactly. Island evolution is a natural laboratory, and it repeatedly shows us that dramatic change can occur rapidly when the selection pressures are strong enough. It's a good reminder that evolutionary timescales are not fixed. They're set by the environment. Search Fossil Goose, New Zealand Giant Birds Evolution 2026 to read the study.
That's a wrap for this week. NASA satellites are watching what may be the birth of a new island in the Bismarck Sea: pumice rafts, steam plumes, and magma rising toward the surface. JWST found an unidentified molecule on both Pluto and Titan that matches nothing in our databases. Mount Etna may be powered by a mechanism that doesn't fit any of the 3 classic models of volcano formation. Astronomers found the oldest quasars ever detected, shining just 670 million years after the Big Bang, and challenging how we think supermassive black holes grew. And a single fossil goose has rewritten the story of how New Zealand's giant birds evolved.
5 stories about watching things come into being: islands, molecules, black holes, and giant birds. The universe is still full of first drafts. Thanks for joining us.
Until next week, I'm Derek.
And I'm Curie. Stay curious, everyone.